how do we deal with bigrams with zero probability? The simplest idea is called add-one smoothing. And let's look at a picture that gives us the intuition of smoothing in general from Dan Klein. So suppose in our training data we saw denied the allegations, denied the reports, denied the claim, denied the request. And so we've computed probabilities. There were 7 total things following denied the, and we can get our probabilities of everything, of each of these things. But we would like to say, well, maybe denied the report might occur. Sorry, denied the report was in the training data. Denied the effort might occur. Denied the outcome might occur. So we'd like to steal some probability mass and save it for things we might not see later. So this is our training data. And this is the maximum likelihood counts, so these things occurred after denied the, and these never occurred. We'd like to steal a little probability mass from each of these words and put that probability mass onto all other possible words or some set of words so that the zeros go away. And the simplest way of doing this is called add-one estimation, or Laplace smoothing. And the idea is very simple. We pretend we saw each word one more time than we actually did. We just add 1 to all the counts. So if our maximum likelihood estimate is the count of the bigram divided by the count of the unigram, our add 1 estimate is the count of the bigram plus 1 over the count of the unigram plus v. And we have to add v here in the denominator because we're adding 1 to every word that follows word I minus 1. So our denominator is increased not just by the total count of times that something happened to word I minus 1 wasn't just all the previous things that followed it, but each one of those got incremented by 1, and there were v of them, so we have to add v to the denominator. So this is the add 1 estimator, probability estimator. I keep using the term maximum likelihood estimate, and let's just remind you what that means. The maximum likelihood estimate of some parameter of some model from a training set is the one that maximizes the likelihood of the training set given the model. So we have some training set, and we're going to, a maximum likelihood estimator that lets us learn a model from a training set is the one that makes that training set most likely. What do we mean by this? Suppose the word bagel occurs 400 times in a corpus of 1,000,000 words. And I ask, what's the probability that a random word from some other text will be bagel? Well, the maximum likelihood estimator from our corpus is 400 over 1,000,000, or 0.004. Now, this could be a bad estimate for that other corpus. Who knows whether the other corpus, bagel, occurs 400 times per million or some other probability. But this estimate is the one that makes it most likely that bagel will occur 400 times in a 1,000,000-word corpus, which is what it did occur in our training corpus. So we're maximizing the likelihood of our training data. So an add-one smoothing, and any kind of smoothing, is a non-maximum likelihood estimator because we're changing the counts from what they occurred in our training data to hope to generalize better. So if we go back to our Berkeley restaurant project, and we add 1 to all of our counts, here's our Laplace smooth bigram count. So now all those zeros that we had have become 1s, and everything else gets 1 added to it. So now we can compute the bigram probabilities from those counts, and just using the Laplace add-one smoothing equation that we saw earlier. And now we've got all of our our add-one smooth bigrams. So we have, again, the probability of 2 given 1 is 0.26, and now all of those zeros have turned into other things, 0.00042, 0.0026, and so on. Now we can also take those probabilities and reconstitute the counts as if we had seen things, the number of times that we would have to see to get those add-one probabilities naturally. So we take our probabilities and we re-estimate the original counts as if they were the numbers that would have given us these probabilities. And we ask, what do those reconstituted counts look like? How much has our add-one smoothing changed our probabilities? So here's reconstituted counts. So we have I is followed by want 527 times, or Chinese is followed by food 8.2 times. These are reconstituted counts. And let's compare them to the original counts. So up here on the top, we have the original counts, and here we have our reconstituted counts. And I want you to notice that there is a huge change. So in our original count, 2 followed 1 608 times. In our smoothed counts, 2 follows 1 only 238 times. So it's almost a third smaller, 3 times smaller. Or Chinese food occurs 82 times in our original counts and only 8.2 in our reconstituted counts. So the add-1 smoothing has made massive changes to our counts, and sometimes changing a factor of 10 the original counts in order to steal that probability mass to give to all those massive numbers of zeros that had to be assigned probabilities. In other words, add-1 estimation is a very blunt instrument. It makes very big changes in the counts in order to get these probability mass to assign to this massive number of zeros. And so in practice, we don't actually use add-1 smoothing for n-grams. We'll have better methods. We do use add-1 smoothing for other kinds of natural language processing models. So add-1 smoothing, for example, is used in text classification or in similar kinds of domains where the number of zeros isn't so enormous.